So now this is our next question, and which is based on the concept of reverse Brayton cycle, and that is also a very important topic and favorite topic for your objective point of view. So I will discuss the important concept as well as some formulas which you have to remember for your objective point of view. Okay. So now first read the question carefully. An air refrigeration operating on a open air cycle is required to produce 25 tons of refrigeration. I have already told in the VCRS chapter vapor compression refrigeration system so many number of times that the RC power or volumetric efficiency are given in the question, which will help us to find out the values of the mass flow rate. Okay. Now with the cooler pressure of 12 bar and the refrigerator pressure of 1 bar, it means the pressure ratio is 12. Okay, it means the pressure ratio is 12. The temperature of the air leaving the cooler is 25 and air leaving the room is 0 degree, assuming the cycle with isentropic compression and polytropic expansion. So it means in this case the compression is isentropic, but here that is polytropic with no compressor clearance. So actually the important point in this case is, what is the most important thing? So first I want to discuss the basic concept of your reverse Brayton cycle. So please try to listen. I will discuss this question also and the possible objective questions also. Okay. So actually in this case this is your block diagram. Okay. This is your block diagram because all the objective questions I will include in this. So please try to listen carefully. Please try to listen carefully. Okay. So this is the roughly block diagram of this question. Okay, of this chapter. So in this case, this factor is called as refrigerator. Okay, refrigerator. Next, this is called as cooler section. This is called as expansion cylinder. Please remember all these things for your objective point of view. And this is your compressor section. So this is 1, this is 2, 2 is entering, this is 3, this is heat rejection, this is 3, this is 4, and 4 is entering and 1 is leaving. And in this case the heat is supplied, in this case the heat is rejected, and your working fluid, you are using air as a working fluid, and that is direction is anti-clockwise direction. So why anti-clockwise? Because from the name of the heading itself it indicates it is a case of reverse Brayton. Reversed means it is a case of work absorbing device. So in thermodynamics you have covered Carnot cycle, in RAC reverse Carnot cycle, in power plant you are dealing with Brayton cycle, now you are dealing with reverse Brayton cycle. So first from the name of the heading itself reverse word is used, so means it is a case of work absorbing device. Next, second thing is it is all the work producing devices are shown in clockwise direction on PV and TS, and all the work absorbing devices are shown in anti-clockwise direction on PV and TS, pressure, volume and temperature, entropy. Okay. So now in this case the 1 to 2 is compression, means isentropic compression, 2 to 3 is constant pressure heat rejection, 3 to 4 isentropic expansion, and 4 to 1 constant pressure heat addition. So now if you will observe carefully, in this case we have changed the name but the process is almost same. If you are comparing with respect to VCRS, vapor compression refrigeration system. So in VCRS we are using in VCRS we are using the word we are using the word evaporator, and we are using the word condenser. So condenser is replaced with cooler and evaporator word is replaced with refrigerator. So condenser and evaporator are the term related with mostly with the phase change. Okay, I am not saying that superheating cannot be achieved in evaporator, subcooling cannot be achieved in condenser. In fact, we have already solved so many questions which are related to wet compression, which are related to subcooling also. Okay, so in your class itself. So now in this case, what is the important? If condenser and evaporator word are given, in that case at least complete evaporation and condensation is there. If you are increasing the size of the evaporator, if you are increasing the size of the refrigerator, okay, evaporator and condenser, then subcooling as well as superheating can be achieved. So because the working fluid is air is treated as ideal gas. For air is treated as ideal gas, okay, air is treated as ideal gas, and for an ideal gas, enthalpy is a function of temperature. So okay, for an ideal gas, enthalpy is a function of temperature, and ideal gas equation is PV is equal to MRT. So it is a gas. Gas means it does not undergo a phase change. If there is no phase change, so that's why we cannot use the word evaporator and refrigerator. Okay, that's why these are replaced with the new words, but the process is same: constant pressure heat addition, constant pressure heat rejection. But now come to this 3 to 4. In 3 to 4, if you will able to recall your VCRS cycle, in VCRS cycle we are using isenthalpic expansion. Okay, in this we are using isenthalpic expansion 1, 2, 3 and 4. Okay. So in the case of VCRS, if no information is given, then complete evaporation and complete condensation. Okay, complete evaporation and complete condensation. So we are using isenthalpic, but here we are using isentropic. So why? In this case we are using isentropic expansion, because if you will use isenthalpic, so H3 is equal to H4. So enthalpy is a function of temperature and T3 is equal to T4. It means there is no temperature drop in the expansion cylinder. If there is no temperature drop, instead of absorbing the heat, it will reject. Okay, so that's why the isentropic expansion is used. Okay, isentropic expansion is used. Isentropic expansion is used in your reverse Brayton cycle. Okay, but why we are using isenthalpic expansion here? Because in this case, what is the observation? In this case in this case, the observation is that if you will use isentropic expansion, so it will not justify the cost of expander. Okay, it will not justify the cost of expander. See, COP is equal to desired effect upon work input. Okay, and work input is equal to compressor minus expander. Okay, compressor minus expander. So in this case, the compressor is an example of open system, so VDP minus VDP. Okay, but I am interested in right now magnitude, and turbine and throttling are also example of open system, so VDP. So compressor, evaporator to condenser, throttling, yeah, isentropic expansion, condenser to evaporator, means the pressure change is same, magnitude, the pressure change is same, but compressor is handling the gaseous phase of the working fluid and turbine is handling the liquid phase of the working fluid. So now observe carefully here, the compressor is handling Vg and expander is handling Vf, and we know that the value of Vg is much higher than Vf. So therefore the expander work is negligible in comparison to the compression work. That's why the isentropic expansion will not justify the cost of expander. Due to this reason, we are not using isentropic expansion in case of VCRS chapter. VCRS, vapor compression refrigeration system. Moreover, the turbine is operating in the wet region. If you are using, so means liquid plus vapor mixture is entering, and it will create an impact on the turbine blades, which will decreases the life of the turbine blades, or you can say that which will erode the turbine blades at a faster rate. Okay, so this is your explanation of your why we are using isenthalpic expansion in VCRS and why we are using isentropic expansion in this case. Okay, and next, why we are using only air as a working fluid? Why? Because of low weight per ton of refrigeration. Okay, because of low weight per ton of refrigeration we are using. Okay, so now in this case, why I have included that question? Why I have included this question? This one, because in this case the one most important thing, the isentropic expansion is not given, that is polytropic. And I have observed so many number of times due to students are solving the question in so hurry that they will miss this word, important word, that in this case the isentropic word is not given. Okay, so now if you will observe carefully that how to draw the TS diagram, how to draw the TS diagram for this case. So TS, okay, so this is your basically TS diagram. So this is 1, this is 2, this is 3, this is 4. So 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So now in this case what is the observation? 1 to 2 process is isentropic compression, 2 to 3 constant pressure heat rejection, 3 to 4 isentropic expansion and 4 to 1 constant pressure heat addition. So actually the COP is equal to desired effect upon work input. Work input is compressor minus expander, and that is H1 minus H4, okay, and divided by this is H2 minus H1, okay, and this is H3 minus H4, okay. So this is H1 minus H4 divided by H2 minus H1 minus H3 plus H4, okay. H1 minus H4 divided by this is H2 minus H3. So just I am separating the terms, okay. Which terms? This H1 and this H4. Take minus as a common, and this is H1 minus H4, okay. So now after this we can see that this is coming out as H2 minus H3 upon H1 minus H4 minus 1. Enthalpy is a function of temperature. So that is T2 minus T3 upon T1 minus T4 minus 1, okay, T4 minus 1. So this is take anything common, either T2 or T3. So 1 minus T3 upon T2, okay, and take T1 as a common. So 1 minus T4 upon T1 minus 1, okay. So but if you will observe carefully this case, so T2 upon T1 is equal to pressure ratio Rp raised to power gamma minus 1 upon gamma is equal to T3 upon T4. So now from this one most important formula is coming into picture, okay. Okay, T2 T4 is equal to T1 T3. So please remember for the objective point of view this formula. This is very important, okay. So what is the shortcut to remember? E1 odd. So T2 T4 T1 T3, but provided that both compression and expansion are isentropic process, isentropic compression and isentropic expansion. So please remember this formula for your objective point of view. So E1 odd. So if you will use that concept here, so what is the concept? T2 T4 is equal to T1 T3, okay. T2 T4 is equal to T1 T3, okay. So now you will get 1 upon T2 upon T1 minus 1, and T2 upon T1 is Rp raised to power pressure ratio gamma minus 1 upon gamma minus 1. So this is the COP of reverse Brayton cycle. This is the COP of reverse Brayton cycle. So the second formula you have to remember for your objective point of view is this, okay. That is the COP is equal to 1 upon Rp raised to power gamma minus 1 upon gamma minus 1. But very important thing, this formula is applicable only when both compression and expansion are isentropic. This is the most important thing which I want to discuss, okay. So and now if you will observe this question, okay, the question are isentropic. First I will write down. Okay, if you will observe, so the compression process is isentropic, but expansion process is not isentropic, that is polytropic. So it means that you cannot use this formula directly, or you cannot use this formula also. Okay, COP is equal to T1 minus T4, okay, T1 minus T4 upon T2 minus T1, okay, minus T3 minus T4. You cannot use this expression also. See, because enthalpy is a function of temperature only for ideal gas, no doubt in that. But from where this expression is coming into picture? Because if you are in so hurry, definitely you will find out the answer by using this concept. But my dear friend, you have to remember the basic also. Thermodynamics, H1 plus kinetic plus potential plus heat is equal to H2 plus kinetic plus potential plus work. So kinetic potential neglected. But what is the basic difference between polytropic and adiabatic? Adiabatic means heat interaction is equal to 0, and polytropic means heat interaction is not equal to 0. So if you are both compression and expansion are isentropic means reversible adiabatic. It means due to this reason the work expression are in terms of enthalpy change, and enthalpy is a function of temperature only for ideal gas. So please don't repeat these type of blunder in your exam point of view. In fact, your all cycles, that is all cycles like that is your Otto cycle, diesel cycle, dual cycle, Carnot, reverse Carnot cycle, Brayton cycle, reverse Baton cycle. These all cycles are depend only on one concept, that in all cycles the formulas are applicable only when both compression and expansion are isentropic. Okay. So now please note down. Okay, now I am giving some seconds so that you can pause and you can write down easily. Okay, and then we will start our question. Okay, and what is the question? This. So now see this question, the air refrigeration system. So the mass flow rate value is given, the pressure ratio, this is 12 bar, 1 bar is given, and the temperature of the air leaving the cooler. So first I will draw the PV diagram. Okay, so I have already discussed the TS diagram. So now I will draw the PV diagram. So now first I will draw the PV diagram, because already TS diagram I have already discussed. Okay, so this is the PV diagram. So now 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay, so there are two constant pressure process. Okay, one is polytropic and one is adiabatic. So how to represent the polytropic and adiabatic process on the PV curve? How to represent? The representation is done by the curve type. Okay, by the curve type. Okay, so this is 1. Okay, this is 1, this is 2, and this is 2 to 3. Okay, 3 to 4 and 4 to 1. So now in this case, what is the game they have played? The game they have played is this compression is, see here, the compression is isentropic, but this is expansion is polytropic. So this is PV raised to power 1.4 is equal to constant, and this is PV raised to power 1.35 is equal to constant, and this is PV. Okay, this is 1 bar and this is 12 bar. Okay, this is 1 bar and this is 12 bar. So now in this case, what is the first thing? You have to draw the PV or TS curve. Okay, and then find out the values of temperature. Okay, so the process 1 to 2 is PV raised to power 1.4 is equal to constant. So T2 upon T1 is equal to P2 upon P1 raised to power gamma minus 1 upon gamma. So T2 upon T1 is what are the temperatures? So now please see here, the temperature of the air leaving the cooler is 25 degrees Celsius means 298 Kelvin. 298 Kelvin, and the temperature leaving the room is 0 degrees Celsius. So means this is the value of T1. Okay, T1 and T3. These are the values. Okay, so the values T1 is given as 273 Kelvin and T3 is given as 298 Kelvin. Okay, 298 Kelvin. So this is 273. This is 12 upon 1 raised to power gamma minus 1 upon gamma. Okay, gamma minus 1 upon gamma. So 12 raised to power 0.4 upon 1.4 into 273. Okay, so T2 is 555.26 Kelvin. Okay, T2 is this. Next expansion, the process. Okay, the process 3 to 4. Okay, 3 to 4 is PV raised to power 1.35 is equal to constant. So T3 upon T4 is equal to P3 upon P4 raised to power n minus 1 upon n. Clear? So there the temperature is 298 upon T4, that is 12 upon 1 raised to power 1.35 minus 1 upon 1.35. Okay, so the index is changed, 0.35 upon 1.35 inverse into 298. Okay, so T4 is coming out as 156.46 Kelvin. Okay, 0.46 Kelvin. So all the values of temperatures are known. Now you can find out the values of work input. So now the process 1 to 2 is your compressor. 1 to 2 is your compressor. Okay, a compressor. So compressor is an example of open system. Open system means n times work of closed. N times work of closed. So n times initial minus final. P1 V1 minus P2 V2 upon n minus 1. Okay, P1 V1 minus P2 V2 upon n minus 1. So n upon n minus 1 PV is equal to MRT. MRT means T1 minus T2. Okay, MRT T1 minus T2. So what is the value of index? 1.4 upon 1.4 minus 1. Okay, so you can use n or you can use gamma, because in the case of work there is no difference. Okay, polytropic means heat interaction not equal to 0, adiabatic means heat is 0, but there is no difference in terms of work. Just replace n with gamma or gamma with n. So index is this. So per kg I will calculate. Okay, and now in this question first I will see mass, air, compressor, piston displacement per minute, expander, coefficient of performance, power required per ton of refrigeration. Okay, so I will find out per kg in this case. So 0.287 into T1 is 273 minus T2 is 555. Okay, 0.26. Okay, 555.26. 273 minus 555.26 into 0.287 into 1.4 divided by 0.4. 283. Okay, 283.5. Okay, this is minus 283.53. Okay, so now units, this is in 1 kg. I have taken kilojoule per kg, Kelvin into temperature in Kelvin. So ye cancel, so you will get in kilojoule. Okay, kilojoule, but I have calculated per kg. Okay, so if after reading the question, if there is a need of mass, just multiply with mass also, so that you will get the answer in kilojoule. Okay, so first I will find out the values of work by per kg. Okay, per kg I have find out the values. Okay, now compressor is over, now expander. Okay, so process 3 to 4. Okay, so expander 3 to 4. So why it is coming out as negative? Because it is a case of work absorbing device. It is a case of work absorbing device. So n times work of closed again. So in this case n upon n minus 1 n upon n minus 1 into mr into T3 minus T4. Okay, T3 minus T4. But here what is the most important thing? The important thing is you have to remember this. I think index is 1.35 na? 3.5. Okay, so 1.35 upon 0.35. Again I am calculating per mass. Okay, after calculation of mass, if there is a need, then I will multiply with mass also. Okay, so don't worry about that. Okay, don't get confused in that part. Okay, into T3 is 298 minus this is 156.46. okay, 156.46, 298 minus 156.46. okay, into 1.35 into 0.287 divided by 0.35, it is coming out as 156.68. so now the most important thing I want to prove, that turbine is an example of open system. Turbine is a work producing, positive work. Compressor is a work absorbing, negative work. Okay, now if you will calculate the net work output, that is minus 283.53 plus 156.68. okay, plus minus 283.53, it is coming out as minus 126.84 kilojoule per kg. So it is a case of work absorbing, because the net work output is negative, it means it is a case of work absorbing device. So many objectives and theoretical question I have proved in this case also. Okay, so the work input is coming out as this. Now we need the values of mass flow rate. Okay, so how to calculate the values of mass flow rate? So in this question some data is given, RC 25 tons. Okay, so RC is given as 25 tons into 3.5 is equal to mass flow rate into refrigeration effect. Okay, or refrigerator. So 25 into 3.5 is equal to mass flow rate into Cp into T1 minus T4. Okay, so the mass flow rate into 1.005. okay, T1 is कितना है, 273 and 156. okay, 273 and 156 point how much, 0.46. okay, 0.46. okay, that is 25 into 3.5. okay, so 1.005 into 273 minus 156.46. okay, inverse into 25 into 3.5, so 0.74. okay, it is coming out as 0.747 kg per second. So now if you want the answer of power input, so mass flow rate into work input. Okay, so the values of work input is already calculated into 126.84. it is coming out as 94.75 per tons of refrigeration. okay, per tons of per tons of refrigeration नहीं, मैंने क्या लिख दिया, sorry this is in kilowatt. okay, this is in kilowatt, because we will check the units. Mass flow rate is kg per second and work input is in kilojoule per kg. So kg cancel out, you will get the power input as 94.75 kilowatt. okay, so the mass flow rate in kg per minute, first part 0.747 into 60, so they are interested in kg per minute, so 44.82, this is coming out as kg per minute. okay, so now we are checking the units only. okay, so according to the question we are solving. okay, so in this case the mass flow rate is given, we have calculated in kg per second, but they are interested in kg per minute, so that's why I have calculated in terms of kg per minute. okay, so 44.8 k around. okay, and this work done, that is 127 k around आ गया, and this total. Now this is the power input, but they are interested in tell me power input per please see here per ton of refrigeration. So there is 25 tons, okay, 25 tons. So it means power input per ton of refrigeration is 94.75 upon 25, okay, 94.75 upon 25. So 0.75 upon 25, this is coming out as approximately 3.79 or 3.8, okay, approximately 3.8 kilowatt per ton of refrigeration, okay, per ton of refrigeration. So now this part is calculated, okay, and power per ton of refrigeration calculated. COP, now you can find out the COP easily. How? COP is equal to RC upon power input, simple thing. So RC is given as 25 tons, okay, so 25 into 3.5 upon power input. The power input is given as 94.75. So this is coming out as 25 into 3.5 divided by 94.75. This is coming out as 0.923. Okay, so the COP is coming out as 0.923. Clear? So 0.923. So अब zoom in कर देते हैं so that now you are able to understand each and everything. Okay, clear? So in this case, first I have calculated the T2 value and T4 value. T2 by using 1.4 index, T4 by using 1.35, and this is given in the question. Okay, I have not taken any assumption. So closed system work, okay, sorry, compressor work. Compressor is example of open system, n times Surkov close. Okay, turbine is example of open system, n times Surkov close, but the index is 1.35. Here the index is PV raised to power 1.4 is equal to constant. Okay, index is 1.4, and this is the factor. Now the last part, two parts are left: compressor piston displacement required per minute, expander displacement required per minute. So how to calculate the compressor piston displacement? Okay, so compressor piston displacement, okay, so many in a single question you are able to understand so many objective question. Okay, compressor displacement, okay, compressor piston displacement, okay, per minute. Okay, so how to calculate compressor piston displacement per minute? Compressor piston displacement is nothing, that is m dot v entry, okay, m dot v entry, and v entry is v1, okay, v entry is v1, or specific volume is equal to volume by mass. So basically you have to calculate the V dot 1, okay, V dot 1. So how to calculate the V dot 1? M dot RT1 upon P1, okay, but if you will observe carefully, they are interested in per minute. So the mass flow rate we have calculated 0.4747 kg per second, but 44.82 per minute. Okay, so R for air is 0.287, okay, into T1 is 273, okay, upon P1 is 1 bar, so 1 into 100 I am converted, okay, so into kilopascal, 0.82 into 0.287 into 273 and divided by 100. So this is coming out as 35.1, okay, 35.1 meter cube per minute, okay, meter cube per minute. We will check the units. The mass flow rate I have taken in kg per minute, R in taken as kilojoule per kg Kelvin into temperature in Kelvin, pressure in kilopascal. Kilopascal means kilonewton per meter square, okay, kilonewton per meter square. So kg, Kelvin cancel. Kilojoule is kilonewton meter, so kilonewton cancel. Meter square into meter cube per minute, hence proved. Clear hua? Hence proved. And expander also. Expander means V4, okay. So Now the expanded displacement required per minute. So for this we have to find out V dot 4 or volume flow rate at point number 4. So now you can find out by using MRT also, but there is one shortcut, 4 to 1 at constant pressure. So PV is equal to MRT. Okay, so V dot is equal to M dot R upon P into T. Mass is a constant, R constant, pressure constant. So V dot 4 upon V dot 1 is equal to T4 upon T1. So T1 is given as, I think, let me check. T1 is given as 273 and T4 is 156.46. 156.46. This is 273. V1 dot is 35.1. Okay, 35.1 into 156.46 and divided by 273, 20 point. Okay, this is coming out as 20.12. okay, so V dot 4 is 20.12, that is in meter cube per minute. Okay, so now I think, okay, now I think you are clear. Piston displacement per minute, volume flow rate at the entry of compressor and volume flow rate at the exit of expander. Okay, indirectly they are asking this, and we can use PV is equal to MRT. Okay, and in this question, what is the most important thing I want to discuss? Only polytropic process. So if polytropic process word is given, in that case please do not use directly that formula COP is equal to 1 upon RP raised to power gamma minus 1 upon gamma minus 1, because that formula is applicable only when both compression and expansion are isentropic. Okay, when both compression and expansion are isentropic. Okay, clear?